Good morning, everyone. Welcome to today's ECE Colloquium. We're really excited today to have Professor Prem Kumar to be our guest speaker. Professor Kumar is Professor of Information Technology in the McCormick School of Engineering at Northwestern University. And as his talk will tell us more, his research focuses on quantum photonic devices and their applications. Kumar was a program manager at DARPA, where he created and managed a portfolio of programs in basic and applied sciences. He was selected Program Manager of the Year in 2015 and awarded the Secretary of Defense Medal for Outstanding Public Service in 2016. He's a fellow of Optica, formerly OSA, American Physical Society, IEEE, Institute of Physics in the UK, AAAS, and SPIE. And since 2020, he's serving as the editor-in-chief of Optica, which is the flagship journal of the Optica Publishing Group for high-impact results across the whole spectrum of optics and photonics. And so we're really delighted to have Professor Kumar with us today. Let's please welcome Professor Prem Kumar.
Thank you, Dan. So first of all, thanks again for inviting me here and giving this opportunity to talk about some things that I feel very passionate about in the last 5-6 years after coming from DARPA, thinking about what's the next frontier that we as electrical and computer engineers should tackle. And I'm going to paint a picture of quantum networking and point along the way what challenges exist and small contribution, kind of baby steps that my group is making. And wherever I talk about my work, it's in collaborations, because I think we need more of those in order to make progress in this multidisciplinary area. So the title of my talk is Engineering Challenging for the Emerging Quantum Networks, emerging because they don't yet exist. The situation in quantum networks is similar to what it was in the 1970s, early 70s, I would say, when small-scale 8-bit classical processors had arrived on the scene, and people like Windsurf and Bob Kahn started to ask, hey, what could happen if we interconnect them through classical communications? And the application of the day was email. And today, just imagine you didn't have email. Every child, takes that for granted. We all take it for granted. File sharing, data transfer, and ubiquitous communication and computing that we all enjoy as we walk around with their smartphones in our pockets. So I will take that analogy and try to put quantum communications and networking in a perspective. Again, forecasting is very difficult in a space that, just like, if you step back and ask yourself, would the founders of computer science, like Turing, Church, von Neumann, could they imagine that we will have the technology in our pockets, back in the 1930s? I venture to say no. But you never know what the future will bring. So anyway, at this point, we will just imagine. I've already said a few things about this. I've titled it as Bit Revolution. Most of the computer science was done, as I said, in the 1930s in terms of the foundations. And there were physical insights there because computers existed 100 years before that, and there was mechanical computers. But the arrival of the transistor and the integrated circuit really pushed this on an accelerating slope, exponential rise. And then, people started to interconnect. The key point there was, what are the device abstractions that are needed for different things to interconnect and communicate? And then many experimental networks were set up. There's the ARPANET, which is well known in history now, and of course the NSFNet. And then in the big data, AI, that's where we live today. So the question then is, and of course, we can ask a similar question, would there be a similar qubit revolution? We have, in the context of quantum key distributions and specialized networks that were funded and demonstrated in the early 2000s, but arrival of 2010s has brought in accelerated developments in quantum computers. I mean, today, one can buy NISQ hardware, NISQ standing for noisy intermediate scale quantum. These computers that are noisy, but yet physically have been shown to do things that classical supercomputers cannot simulate. So given the investments, both private and government, that has gone on, it is likely that in the near future, there will be places that will have quantum computers. And maybe those are big labs, maybe those are big centers. But nevertheless, we can start asking the question, would a quantum internet emerge if we start to think about how to interconnect these emerging quantum processors, general purpose, NISQ machines, or whatever quantum hardware that might emerge? So the point here again would be that we need to know, how should we network them? How do we interconnect what the architecture is? And more importantly, we need to develop those abstractions that would allow us at least to architect and project in the future what kind of applications a network quantum system would allow, and then what requirements it might have that could guide device development and hardware development along the way. So in that sense, we are at the similar stage as we were in the 1970s. So that's the backdrop around which I would like to discuss a little bit more in depth. And in depth here means for the students. And certainly this talk is going to be at a fairly high level, except when I talk about my own stuff, which I might go into a little bit more detail. So let's start thinking about what do we mean by communications. And it's good to review what classical communications and networking is. Well, in classical communications, there are two parties, and often in the language of cryptography, or one labels them Alice and Bob. You have a device in your hand. It could be your smartphone, which has a register which has classical bits of information, classical bits which can only be in states 0 and 1. And you have somebody else, your friend Bob, who you want to communicate that information to. And long ago, again in the 1940s, Claude Shannon showed that irrespective of the distance between them, that it's always possible to do error-free communication below a certain capacity. And that capacity depends on the characteristics of your channel. And of course, recently, Shannon's a movie about him has been made and popularized. So the question, and of course, that was the beginning. And today, it took a long time to develop the codes to make that realistic. But today, classical communications and networking is ubiquitous. You look at a supercomputer, it is lots and lots of millions of processors interconnected by high-speed communications. You have data centers, which are giant communication networks. And then, of course, we have global connectivity with fiber optics. And on the right is the edge connections through wireless communications to our handheld devices. So can we imagine something like that happening with quantum? I think that's a wide open future. If that could happen, it will be this Star Trek holodeck in some ways. But nevertheless, it shouldn't stop us from imagining. So let's extrapolate if that is possible. So now I imagine Alice and Bob, instead of that classical device, this register here is a register of quantum bits. these quantum bits can be in superposition states. Not only they can be 0 or 1, and you can encode them in hardware based on various different technological platforms people have these days. The important thing is that they can also be in a superposition, which often colloquially one talks about a Schrodinger's cat, which is simultaneously alive, and that unless you look. So can we, by the same extension, have quantum communication between Alice and Bob so that Bob gets the same quantum state that Alice possessed in her qubit register? And if you naively think about this, and you find that that's not possible because that immediately leads to conflicts with quantum mechanics. Quantum theory is linear, and there is the so-called no cloning theorem, which you can, if you Google it, in half a page of proof, you can show that it is not possible to duplicate an unknown quantum state. Here, if a qubit in Alice's possession was part of some kind of a quantum computation, you don't know what it is, so it would be an unknown state, and you cannot really create a copy of it in Bob's possession without doing something to Alice's qubit. Even a measurement and send strategy doesn't work, like the old fax machines where, okay, I'm going to measure every bit and then recreate that, having the resources of a paper and an ink on the other side. So, like the Star Trek transporter, for example. Even that doesn't work because there's Heisenberg uncertainty principle comes in the way that it is impossible to actually reconstruct a quantum state. It's to know on a given copy. So it seemed like this was a no-win situation until, of course, Bennett and co-workers back in '93 came up with this teleportation protocol. What they theorized was that if Alice and Bob could pre-share what is now called an entangled pair of qubits. An E-bit, or entangled pair of bits is an E-bit, one half in Alice's possession, the other half in Bob's possession, but those qubits are entangled with each other. If that is the case, then Alice makes a joint measurement, which is often referred to as a Bell state measurement between the qubit she wants to share or teleport to Bob and half of the E-bit entangled pair of bits, the one in her possession. That's a 2-qubit measurement. That's something that's challenging to do, but nevertheless it can be done. When you do that, your outcome is 2 classical bits of information, 4 possible choices. And if those are communicated to Bob, then it turns out that Bob can use that information to transform his half of the entangled pair of bits, the half of the E-bit that he has, into the state which Alice had in her possession without actually measuring it. So this teleportation protocol recreates that qubit from Alice to Bob, and Alice, because she made her 2-qubit measurement, her information completely disappears. So this protocol then showed that how quantum information can be moved from one place to another by utilizing an extra resource of entanglement. Okay, so that resource then becomes very important if you want to communicate quantum information from location A to location B. And imagine now if you want to interconnect, then entanglement factories would be needed. They have to be ubiquitous and commonplace. And one needs to have a network that provides entanglement distribution service, teleportation service to build future applications on. So that's the kind of scenario that everyone envisions. And it is very challenging because listed here are lots of things that one needs to do. As I mentioned, you need to have ubiquitous availability of, and I'm focusing on photon pairs because to go over a distance, although you can have qubits that are entangled in other modalities, but it's only the photonic qubits that can be transmitted over long distances. And even long distances, meaning distances on the order of meters or longer. And then you need to have efficient distribution of that entanglement because you could create a good quality photon pair, but by the time you distribute it, your quality may degrade. And of course, you need to be able to store that so that they can be used whenever in the future in this so-called connectionless quantum communication, where at the time of teleporting, you can recall that cube, the half of the entangled bit, and make the measurement and send the results. And then, of course, there are all these other technologies that I've mentioned needs to be had. And of course, efficient detection of those Bell states. Even now, in the photonic world, we can't have all 4 Bell states being measured simultaneously. A lot of the applications that you hear about rely on a partial measurement of those Bell states. And in the transmission, in the distribution of this entanglement, of course, there's loss. Even fibers, even though they are very low loss, they still, if you go 100 kilometers, you still lose 90% of your light. So there's 90% probability that your photon is going to be lost. And of course, decoherence, which for photons is not that big of an issue, but nevertheless, if you want to go global distances, it is an important issue to be tackled. And of course, one can also talk about operational challenges. Today, we take classical networking kind of ubiquitously, but underneath there is a lot of infrastructure that's taken care of. One would have to evolve that kind of an infrastructure. For example, how does one manage these entanglement factories? How do you control it? How do you provide the services and so forth? Again, that's just notional questions here. It's too far in advance to really speculate on how this would work. But one needs to keep in mind that as technology progresses, how we're going to handle these kind of questions. Okay, so that's kind of the overall big picture. And what I want to show you now is some of the small contributions that we have made along the way in terms of going towards communications and networking. So my interest in this started back in the 1990s, where I was working on actually classical optical communication devices, erbium type amplifiers. Those of you who are in optics know that there is such a thing as erbium doped fiber amplifier that has made truly the global reach of the networks possible. Because this fiber has loss, as I said, over 100 kilometers, you lose 90% of the light. So periodically, you have to boost that signal, and once one does that by means of an optical amplifier. Those optical amplifiers have a bandwidth limitation. There's only a certain spectrum of light that they can amplify. But today, and even then, the demand for information was growing. In data centers, you need bandwidths of hundreds of nanometers. So this is hundreds of terahertz, 500 terahertz or petahertz kind of bandwidths are needed. So the question was, can we invent some other type of amplifiers? And we were working on utilizing the nonlinearities of glass to build what's known as parametric amplifiers. And again, I don't want to go into the details of it. This is standard classical optical communications and nonlinear optics. We have a lot of literature that we've worked on. Most well-known of this is the so-called microstructure fibers that spawned a revolution in frequency combs and type of lasers, merging continuous wave laser technology with pulse laser technology, and that's an area that has become really important and popular in its own right. But what we observed was that when you put light into these fibers at a very specific place, so-called zero dispersion of the fiber, you see these so-called side bands. You see these things pop up on the right and left. And that have been known, again, in the classical nonlinear optics literature as modulation instability side bands. But no one actually asked the question, how do these side bands start? And my intuition at the time was that they have to be photon pairs. So lo and behold, we did experiments. We built photon counters in the telecom band where this work was being done. and showed that this process actually is very similar to the so-called parametric down conversion thing that's in our logo here. A pump photon comes in and then spontaneously converts into two daughter photons, and because they are simultaneously born, the daughter photons, they get entangled. The same thing can occur in fibers by pumping it at the right wavelength, and you have instead two photons that interact through this nonlinearity, and they get frequency shifted a little bit. One upshifts, the other downshifts, energy is conserved, but they have the same properties of entanglement. Okay, and that led to several experiments that we pioneered. We built several photons pair sources based on this, and again, I think in this setting, I don't want to go into the details, but if anyone's interested, I can talk about this, how these photon pairs are generated. Basically, you create an indistinguishable pathway between a pair of photons that are born, so let me click that, going clockwise through this piece of fiber and then going counterclockwise through this fiber. When those pairs of photons are born, you don't know whether they got born in the clockwise or counterclockwise fashion. And that indistinguishability can be built into entanglement. And in this case, we generate polarization entanglement. And of course, we have to cool the fiber because at room temperature, there is another effect that goes on, spontaneous Raman scattering. Again, that's a detail. Those of you who are interested, I can talk about it. But the point is that this was commercialized back in the early 2008-9 timeframe. And you can put all this stuff in a box and take it into the field and do these kind of experiments where you are creating polarization entangled photon pairs in the telecom band on the standard ITU grid and start doing experiments. And we did the following experiment. This is a lab experiment done in 2006, way ahead of its time, where we had a polarization entanglement source that I just alluded to in the previous slide. And one of the photon pairs at these wavelengths that are marked, these are ITU grid wavelengths, was multiplexed in with classical light bearing classical 10 gigabit per second data, multiplexed in on channels that are very nearby the same quantum channel, and propagated 50 kilometers on one side, the other photon of the pair, 50 kilometers on the other side, also in the presence of a different classical channel. So these photon pairs, they are demultiplexed out. Now they are 100 kilometers apart, and yet they have higher visibility than is needed to violate Bell's inequalities and various other quantum applications one might want to do. So this was work as a post-deadline paper in 2006, that you could do 100-kilometer polarization entanglement distribution in the presence of classical light on the same fiber. This is not dark fiber. But of course, this is done in the lab. And it has taken 15 years to convince somebody to take this out of the lab. And now, because quantum computers have made remarkable progress over the years that people have started to talk about, that we need to interconnect them. So the kind of technologies we want to work on have been demonstrated in the lab to build networks that can do entanglement distribution, that can do teleportation, that can interconnect quantum hardware over a distance. Clearly, 100 kilometers is kind of the limit at this point, or metro scale is kind of the limit, because we still don't have the technology that's equivalent to that optical amplifier that took metro scale networking in the classical world to global networking. We do not have a quantum amplifier, which is not possible because there's no cloning theorem, but people do talk about quantum repeaters. That's a slightly different technology, but on paper they exist. We don't have any even in-lab implementation of those yet. Yes?
Just a naive question. So at the time, this 50-kilometer fiber, was that a commercial fiber somewhere in the ground?
No, this was in the lab. That's a spool of fiber in the lab. 50-kilometer spool of fiber in the lab. I'll show you an experiment which we've done in ground fiber now. Okay, so we still don't have optical repeaters, but I think time is right to start building networks, answering some of the questions of how are we going to manage and control these kind of networks on the metro scale. And that is something that we are currently implementing. This is a project we started a couple of years ago in collaboration with Fermilab and Argonne Lab. These are the two national labs in our neighborhood. And the goal there is to set up, to demonstrate that you can provide some kind of a quantum service in the metro completely under computer control and with all the layers, the protocol layers that are needed, but in a regional network with current devices that are possible. That is, ignoring transduction devices, ignoring repeaters, but yet build things in a way that those could be incorporated if breakthroughs do occur. So in this experiment, in this project, of course, as I've listed here, is exactly what I said in other words. So we want to use current technologies, but work in a way that we have a networking scenario. So the network that topologically, it consists of 3 sites. One site is at Fermilab, one is at Argonne, and one is at Northwestern. Each site has a local area quantum network, because that's how we envision. These don't exist yet, only parts of it exist. But that's our vision. So for example, so this is the physical layout. So my labs are over here in Evanston, and we have a Chicago campus where we have another switched hardware, so we can do experiments going from my lab to the Chicago campus and back. And we have connections through this Starlight facility to a couple of other places nearby, and then to Argonne and to Fermilab. These connections exist in principle, but they're too far for now to do any realistic experiments on yet. And so here's a little blow up of that region in the box here. So that's the physical layout. And again, I've already said this in other words. I want to make a point about why we need to go beyond dark fiber interconnects. The point in my argument is actually very simple, and potentially somebody could poke holes in it. Most of the fiber that we use, even the fiber that we have access to in the Chicago area, the physical layout that I showed to you, these are all leased fibers. People who operate communication services, they don't own their fibers. They lease them from people who install those fibers in the ground. So if I am that company that is renting or leasing my fiber to you, I would charge you for the same amount of money for the dark fiber as I would charge for that fiber carrying 100 terabits of data on the traffic. That's going to generate me a lot of revenue. So the cost of the dark fiber is just going to be that. So if ever in the future you want to commercialize, dark fiber-based networks are going to be incredibly expensive. Not only for the hardware, but just leasing the dark fibers themselves. So I think it is important that we should explore ways of using the same fibers for the classical communications infrastructure as you do for the quantum communications. And in fact, as you saw in the teleportation protocol, you do need to do classical communications after you've made your Bell state measurements. Maybe there's a node that has a measurement node, then the outputs have to be communicated to other nodes where that information is going to be used to have those teleported photon pairs available or put into memories and so forth. So addressing classical and quantum information infrastructure, coexistence of classical and quantum information on the same fiber is a very important topic that we must address. And as I showed you in that 2006 experiment, it is possible. It's just that we need to be careful about how do we utilize the fiber, its properties. We need to understand the properties of the fiber in much more detail that have been understood in the context of classical communications. So for example, I alluded to Raman scattering. That's why we had to cool that fiber. Raman scattering is a process, a nonlinear process that's utilized in communications to go beyond that the bandwidth limit of erbium-doped fiber amplifiers that I had mentioned. Raman amplifiers are used in classical networks all the time. But because they are used in classical applications, one focuses only on their gain region wherever the Raman process is of highest efficiency. But for coexistence, we need to make sure that classical channels don't scatter light because of the same Raman process where my quantum channels are. And so understanding the fiber in these newer regimes is important. And in fact, so here in pictures is our focus. So shown here on the right is that gain peak of Raman process in the fiber. And this in the experiments I'm about to show you, we take our quantum channel to be in the so-called O band. That's where the 1300 nanometer region where the dispersion of the fiber is pretty flat. People use that in communications these days for short distance communications or supervisory channels and other things. But I think that's a prime candidate to become quantum channels because they are far on the anti-Stokes side and there is very little Raman scattering that comes into play. And so with that in mind, we've implemented as part of that project that I showed you, quantum communications creating polarization-based multi-channel entanglement in the O band around 1300 nanometers and coexisting that with classical communication channels in the C band, the traditional 1550 nanometer band, and actually shown that you can go from my lab in Evanston through in the basement, wherever the classical networking infrastructure is, go all the way to Chicago. And instead, we don't have all the facilities on the other end, so we just loop it back to the lab and make the measurements there. And so here is an experiment we did last year where our source is still spread out on the table, but that can be put into the box as I've shown you before. And then one of the photon pairs, we hold it locally. And so it goes this way. And the other one gets multiplexed with this C band or 1550 nanometer light and propagates to Chicago and back. So that's a round trip of about not 100 kilometers, it's about 45 kilometers, but is embedded in ground fiber. And then we show that you can do the same kind of a two-photon interference with high visibility that's back-to-back without going. And the bottom one is a transmission over 40 kilometers and back, but no classical light yet. And then here's the data with, on the left, the same data on the previous chart with no classical light. And here on the right is classical light of about 7 dBm of power, which is enough power to at least do terabit per second communications. And the visibility drops a little bit because there is still that residual Raman scattering that contributes. But our recent experiments are showing that you can put in at least 10 dBm of coexisting light along with O-band type of quantum communications. So there's, of course, lots needs to be done in this direction, but I think this is an important area that we must work on if any type of quantum service is to become viable in the future. Otherwise, they will remain as experimental networks. That's my view. Okay, so I want to talk a little bit more about another collaborative project that I had with Ben Yu at University of California, and all of this appeared, these collaborations that I want to talk about emerged out of this QLCI proposal that I led 2 years ago. Unfortunately, we were not those 3 that were selected, but we were among those 6 that made to the reverse site visit. And as part of that, I had created a lot of collaborations, and eventually, since that wasn't funded, we've turned that into small-scale projects that are funded now, and we're trying to make progress. So one of the things that, if this classical quantum coexistence has to be networked, then the signal and idler photons have to go to different locations. They're going to be in different fibers. So we need to wrap them around with classical information, which will tell us what might have happened to those qubits. So this is a protocol that we call quantum wrapper networking. And the idea here is, so this is a recent demonstration that we just presented at the ECOC. This is the European Optical Communications Conference, and we have another paper I'll talk about. We just submitted to next Optical Fibers Communications Conference. The point here is that you have imagined some kind of a network that has network control and management, and you have different parties interconnected, and then you want to do your quantum information needs to be routed through in over some connection that has been set up. So you want to wrap your qubit with classical information as a header and potentially an optional trailer that can carry information on what is the type of entanglement is that qubit carrying, or as the path grows, what is the characteristics of the channel that it's going to go through, or where is the other photon that it's correlated or entangled with, where is that going, so that you can keep track of all those paths, and eventually when the Bell state measurement is made, you can correlate the right measurement. Otherwise, timing. In classical networks, clock and data recovery is the standard chipset these days, because you only need to recover a local clock to decode your data packet that may be a microsecond long, maybe millisecond long. So you need relative clock accuracy. You don't need a global timing infrastructure. Here, your other photon may be going somewhere else. So you do need some kind of a global timing distribution system along with your networks. How does one get that? So here's a wrapper networking protocol would allow you to actually keep track of that timing. Or other characteristics. For example, if you have polarization entanglement, what happens to birefringence on those two different paths and so forth. So this is very similar to in classical world. There's the data label switching. These kind of things are practiced in software-defined networks these days. So we have these wrappers, and then there is the quantum payload in there. So imagine, you come to a switch, you can take off the wrapper, the data goes unmeasured in a different path. You can change that wrapper and add new information to it, and then off you go into the direction where you need to go. So we try to implement that in the lab. This is work again with my collaborators at UC Davis. So they bought some classical hardware, single photon detectors are commercially available, and entangled photon sources are commercially available. There are many vendors that will actually sell these things these days. We set up an experiment where you would create these polarization entanglement, again, multiplex in classical information now as headers, and there is a quantum payload in here, and then there is classical header. There's no information here yet. It's just pseudo-random bit modulation. And then in here is the single photons that are wrapped around with classical information. And we show that you can use classical bit error rate as a marker for the health of the qubit. So this is the same qubit, the same classical information that would go with the entangled photon pairs, and its fidelity can be mapped by just looking at the bit error rate of that classical information that it's carrying around it. Of course, when we go through the fiber, the timing issues start coming in. Here the peak is very narrow. Here the timing is spread out. That's again because the fiber fluctuates over time. And now we also need to recover the clock based on that classical headers, which is our next step in this case. Another thing which I want to talk about is creating these entangled photon pairs. So far, you saw those boxes from Oz Optics that I showed you, or the box that we tried to commercialize in the company back in 2007-8 timeframe. But we need to make them ubiquitous. We need to make them in those small chipsets that can be had for $100 a piece as opposed to $10,000 a piece. So this is a collaboration again coming out of that QLCI proposal, where we're utilizing the standard foundry CMOS process, the nonlinearity in silicon, to do this spontaneous four-way mixing like the one in fiber I described, but now done on the same circuits that are doing other things. So this is electronic photonic quantum integration. So here again, this is a chip that we've put together, and it has a ring. It has all the filters. Everything is included. The idea here is that you will have a small form package to which you only supply DC power, you supply DC light, and you supply some control electronics, and it would spit out photon pairs at your desired wavelengths. That's all. And then they can be utilized in whatever application. In some sense, you build it, the applications will come. I mean, that's the kind of idea here. Of course, for the communications and networking, that's what we are thinking, at least for our near-term application. So here, this is a cartoon. So I will show you basically, you pump it, your DC optical power, it's filtered out to clean up, and then it goes into a ring resonator in which a nonlinear interaction occurs. The signal idler photon pairs are born, and then they get filtered out right on the chip by means of other set of resonators. And then the signal photon comes out on one side, the idler photon comes out on another side, and they are coupled out by the light is the pump light, and the signal idler photons are coupled in and out through grating type of couplers. And we built that, and we've characterized this, and the electronics is all built in. So for example, here we have the pump light is measured, so that the wavelength, the ring resonator locks to the appropriate place, and then when it locks out, everything is automatically stable. It's controlled by FPGA electronics, and then you look for coincidences. There's a coincidence window of about 400 picoseconds, and if you make measurements at that place, you get this quantum correlation with a coincidence to accidental ratio of about 40, which would have visibility if we were to do two photon interference at the same scale that I showed the results I showed you previously. So that's another example of collaboration with trying to make resources for quantum communications and networking that could be commercialized on mass scale. So I think with that, I want to conclude. So the points that I've made here are what I've emphasized in this talk. I think time is right to provide some kind of a network service by building actual networks. What the use cases would be for these networks depends on what kind of a hardware would emerge on the nodes. If quantum computers become available, then certainly those can be connected at the endpoints, and providing entanglement distribution and teleportation, one could try to interconnect those computers together. Perhaps quantum memories could be on the nodes. Maybe it's a distributed storage network. Again, I think jury is out on what kind of applications might emerge. But there are challenges along the way. So pairwise synchronization, as I alluded to, we do need, it's not really global exact time distribution, but we need to recover timing and keep track of where the photons are as they propagate in different parts of the network. And I introduced this quantum wrapper networking protocol. This is, again, a way to make sure that the photons, as they go through the network, its health is deciphered through auxiliary channel. In some ways, it is, when we have VIPs going through one place to another, you do send out scout teams or something that makes sure that everything is safe around as you go around. So that's the vision that I often think about. And then, of course, if you want to commercialize it, then we need monolithic integration of electronics, photonics, and quantum things together. I didn't talk about quantum transduction, and in my conversations with people, these are important technologies if you want to use superconducting transmon-based devices with photonics. That hardware is very challenging. We don't have any work on that, but I think I've thought long and hard about these things. So if anybody wants to discuss that, we can do that. In fact, on November 3rd, next Thursday, Optica, the journal that I'm the editor-in-chief of, we are hosting light conversation with Hong Tang of Yale University, who's a leader in these transduction devices, as a one-on-one interview based on where the technology is, and if you want to join that. And of course, quantum repeaters I alluded to in the talk. I think with that, I'm going to stop and take questions.
Thank you for that really interesting talk. We have time for some questions.
Yes.
So if you were to focus on the idea of small-scale networks for building a larger quantum computer, for example, so you just wanted to connect quantum chips. What you've talked about mostly is the long-range stuff and that challenge that brings. So how much of that gets simplified if you just think about sort of the data center type network, but are there new challenges that arise in that smaller scale?
I think they're very similar. So, people have argued, in fact, there are experiments people have done where you would take, superconducting-based technologies, put a dilution refrigerator in one room, another one in the other, and they are connected with copper coax, but sitting at 10 millikelvin. So that's one way to distribute them. That will be expensive. As you can imagine, now you have to cool those wires. But let's say the distance is, 10 meters, somewhere between 10 to 100 meters. You still need to bring them, if you want to do that wire at room temperature, you have to convert that quantum information from microwaves to optics. And so you will need that transduction device. Once you have that, fibers are low loss enough that whether you have 100 meters or a kilometer, it makes very little difference. So I don't see much difference in the connectivity near term, near meaning in the context of a data center versus metro scale, where one is perhaps somewhere around 10 kilometers apart, maybe 50 kilometers. So on that range, I think the challenges are very similar. Yes.
So following on Greg's question a little further, if you're looking at, I can see a lot of what you're doing applied to terrestrial when you're doing stuff within the planet. Once you get undersea cables, you're going to have to get those amplifiers there, which means you can't use the classical undersea cable, optical cables for doing this. So what's your approach there?
So undersea, I think right now, until those repeaters come along, is unthinkable at this point. So once you have the repeaters, then I can imagine quantum channels being bypassed. I think, again, I'm very speculating there because undersea cables are even more expensive, and there's lots and lots of traffic on them. And being able to figure out where you're going to put the quantum channel, which you're going to have to bypass those amplifiers and put another repeater somewhere, it's going to be challenging. I haven't really put much thought into that because I'm not really thinking that we're there to go this transoceanic distances yet.
I may just one follow-up question. So
Yeah.
It looks like you're running into similar conditions early on in the wave that people try to go to ways not to do an OEO conversion.
Yes.
But you're going to have the same thing.
Yes, so our goal here, I mean, we can't do OEO, period, right? I mean, OEO is that repeater that you need to build. So right now here, there is the photons from the birthplace of the entangled photons to where they get decimated in the detectors. They should be completely transparent as distance would allow.
I'm very interested in your quantum wrapper networking idea. My lab is also doing something like along that way. I'm curious, your proposal is to use a classical photonic header to detect the error rate, and then which tells the payload, which is really entanglement photons, how good the quality is. Well, we know the channel may cause different fading.
Right, so this is just a proof of concept. I mean, that's the experiment we just did. I mean, in reality, I mean, we have a filed patent on this also, on the whole protocol. There's lots of things that you can put on the wrapper. I mean, I alluded to some of the information that needs to go in there. Depends on the type of entanglement and depends on various other parameters, yeah.
Do you think it's okay to put some pilot entanglement photons in the header because you want to check how the channel impacts the photon polarization and that's more related to the payload than the classical payload?
Right, because in fact, the whole point of doing the quantum wrapper is not to do that, because those entangled photons are very precious. Whatever I have, I don't want to put them in the header. I want to use them as payload. Right. So in the QKD networks people have worked on in the last decade or so, they are deriving timing information from the same photon. You sacrifice some of the data or recover the timing as much as you can from those single photon detection events. In the end, if you want to use a certain amount of the quantum bits for extraction of information about the network health, then that data can't be as part of your quantum communication network, quantum communication data pattern and so forth. Yeah, classical encoding is cheap, it's ubiquitous, available. So we want to do as much as possible on the classical. Even in many other things that I've not talked about, everything one wants to do for controlling quantum hardware, quantum packets, data, whatever, should be done in the classical side as much as possible. But decipher from that what would happen to the quantum, including in frequency conversion and information processing and all that. There are certain ideas there. Yeah.
My name is Prem. I'm a PhD student in electrical engineering. I design antennas, and my question is from the electromagnetic physics perspective. I also have a concurrent appointment as a graduate fellow at NASA's Jet Propulsion Laboratory. We are currently looking into quantum radars. You see, in outer space, temperature is really low. So we're looking into trying to see how it will be useful in low-range radar, because high-range radar is still for the reflected photon to come back and the idle photon that is to measure, that is still a problem where the photons getting lost. But for low-range radar, especially in imaging, where we are trying to move, right now the focus is moving from visible spectrum, and James Webb Telescope took it to IR spectrum. We are trying to move it further low, where photons can detect. So, what is your perspective on that? May I know? Thank you.
Yeah, I think people talk about this quantum radar a lot. In fact, the problem with that scenario is that it is very difficult to. So in the quantum radar world, the hype is just incredible, and I can talk offline because I've done workshops on this where we've written reports. including at NASA. We had a very high-level workshop on quantum sensing just last month. The problem is that proof of principle experiments have been done at optical wavelengths, where this quantum illumination is what you're referring to, where you have an entangled photon pair source, you hold one photon locally and the other one goes and interacts and return comes back. It only gives you the advantage when the object you're trying to detect is buried in classical noise. You need very large background noise, and nothing at optics has that features. So people talk about microwaves, where you have a lot of ambient, room temperature noise, whether in space or elsewhere. Then it turns out that holding that entangled photon and making sure that the return comes in and you can do the correlation measurement, it is extremely challenging. A lot of experiments have been done, but I think even Jeff Shapiro at MIT, who proposed this quantum illumination protocol, admits that it will never work in reality. I mean, he wrote it in Science 2 years ago. I can refer you to that paper. In space, where the temperature is extremely low and near range, where you're referring to, it might be that there are conditions that are just right. So that's a very exceptional scenario. So I don't know if some of the challenges that exist for terrestrial applications go away in space.
Temperature is less than 2 Kelvin.
Yeah, of course. So that and, you say near range. So it's possible that there are scenarios that are worth looking into, particularly in the imaging context. I'm not familiar with the details there to really make any informed answer. Yeah.
Any other questions?
I'm looking at more of the practical applications of what you're trying to do. And I look back and look at, I've been about a lot of fiber networks and stuff. And I see you're trying to then see a hybrid between classical networking and what you're doing. Where in there do you take into account all the variation between doped fibers, engineered fibers, and everything else that you have? Because as you said, most people are dealing with IRUs with these fibers. So how do you see the practicality of applying it to the existing position?
Right, but I think the infrastructure we are looking at for fiber are transmission links, right? So I'm assuming that if there is an amplifier along the way, we will need to have a bypass. So that would have to be modified. So so far, if you want to go beyond the metro networks, then a lot more needs to be done. So clearly, if the coexistence scenario is being imagined, then we will have to patch those amplifiers. So maybe one would have to separate the quantum signal and have a quantum repeater here if the repeater is available, and then the classical sees the standard amplifier and they get combined again. It's too speculative, and I'm just cooking it up as we talk. Okay,
great. If there are no more questions, let's thank our speaker once again.